All right. Well, thank you so much for attending the talk. My name is Julien Vanegue, and I'll be presenting on Automated Exploitation Grand Challenge. First of all, I'd like to thank Rodrigo for getting us all here, and the whole H2HC crew for making this happen. Thank you very much. I enjoy my time in Brazil every time I come. So, what is the Automated Exploitation Grand Challenge? We've had some academic research in the past few years regarding the topic of automated exploitation. We've got plenty of very strong claims saying that such a problem is tractable, that kind of a theoretical model involving all the protection that we have today in operating systems are possible, and generate exploit automatically is now a reality. The goal of this talk is to mitigate this a little bit and try to break the myth of automated exploitation. In fact, we've had a list of outstanding problems, a list of open problems that we still need to resolve in order to call it a day. And that's what the talk is about. Before, I'd like to acknowledge a good amount of people that I've been working with in the past, that I interacted with in the past. So many of them taught me what I know today. And I probably forgot lots of people, but these are the most important people in my life. No, I'm kidding. My wife and my kids are actually more important than but, all these people are actually the inspiration for such a challenge, the Automated Exploitation Grand Challenge, and I'd like to acknowledge all their contributions. What is automated exploitation? I like to call it, the ability to generate in a streamlined way, so automatically, without or with few human intervention, the ability to generate a computer attack. When we talk about exploits, there are many domains of exploits. You've got network exploits, you've got web exploits, kernel exploits, system exploits, hardware exploits, application level exploits. It's a huge topic. For this talk, we're going to focus on the software part, the software security, in particular, all the application level security, memory safety kind of exploits. So I'm not going to talk about things like cross-site scripting vulnerabilities, or like a web injections and things like that. Even though such vectors can also be very damaging sometimes, I'm not going to talk much about that today. I'm not going to talk about weird machines today either, but it's important just to try to formalize this concept, and Sergey Brat is just in front of me, and his crew of students have actually worked very hard in the last few years on defining what a weird machine is. And the kind of easy description I like to come up with is the following. It's the underlying capacity of a program to perform runtime computation that escape the program specification. Let's distinguish, two classes of weird machines. One is when computation actually violates the specification. In that case, we can see the weird machine as a security exploit, or inversely, we can see the security exploit as a weird machine. And sometimes as well, the computations, are not intended, but they are compatible with the specification of the program. This is slightly different. In that case, it's more like a covert execution of the program. It's like the program is doing something it's not really supposed to do, but there's no corruption. It's just something happens on top of what the program is supposed to do. And I believe in the future we're gonna talk a lot more about weird machines. So today we talk about weird machine in a binary format. We talk about weird machine in page faults and such fancynesses. And today I'm going to focus mostly on the exploit part of that. So try to understand what represents an exploit when you look at the program from the structural point of view or from a semantic point of view. Today's exploit techniques. it's, as a matter of fact, people know how to write exploits nowadays. We've got plenty of exploits, mostly using techniques such as code reuse attacks, like famous returning to libc, now rebranded return-oriented programming after 15 years of Solid Designer's original post on Backtrack. But that's cool. Everybody needs to have their piece of credit, I guess. And this has been a major attack technique in the last 10 years, I want to say, because we have all these mitigations and getting stronger and stronger, such as ASLR, address space layout randomization. People need more and more what we call information disclosures. Information disclosures is a result of the ability of an attacker to read content of a remote target process. May it be the value of variables of that process or addresses of variables or code, so that you can, for example, craft things like ROP payload, return-oriented programming payloads. People usually force information disclosure. You can have lots of types of information disclosures. I know the PAX team talked a little bit about structured paddings and things like that. So we had a little bit of an overview of what information disclosure can look like. You can also force information disclosures, not like they are bugs in the program, but you can generate information disclosures from other vulnerabilities. For example, one can turn a buffer overflow into an information disclosure. We've seen in the past things like return into printf kind of attack, where you'd actually return into a function that will output some internal program information for you to use on a second stage exploit and do your return-oriented programming based on the guest addresses. And more recently, maybe like 3 years ago, people start to come up with things like just-in-time compiler attacks. This kind of attacks is based on the fact that it's possible to generate new code on the fly, and therefore, if the new code is not generated at randomized address, or if it's possible to guess the address of the code that you're generating on the fly, then in fact you almost don't need an information disclosure anymore, because you can craft gadgets on demand. So that's another kind of attack that people came up with, like Dan Blazakis and many Hi-Fi Lee for Flash, many others as well. When you talk about an exploit, exploits are very complicated objects. However, basically what people are trying to achieve usually with exploit is to obtain a write primitive. A form of a write primitive, it's a slightly simplified form, but the intent is to get the message passed. You have a general form where you have a base pointer plus an offset that is written a value, and you got a dereference happening, so maybe you've got indexed addressing, maybe you got like a base and scale addressing and things like that. I don't display all these details here, but basically a primitive that people try to achieve by exploit is to control such unit of execution in a program that they're trying to attack. We've got many cases. Sometimes the attacker controls the base pointer, sometimes they control the offset, sometimes they control the value, many at the same time, or none at all. And this is very important for exploits. If one controls the base pointer, it's pretty much game over. It means that somebody can actually write everywhere they want. Sometimes the control is just partial, so don't take this as a blank statement. But if you control the base pointer or the offset in such primitive, usually as an attacker, you're in a pretty good position. If you just control the value, that's another story, because usually you can't write everywhere you want. You can just write what you want. Sometimes it's enough. In a really rare case, it can be enough, but usually it's not enough. And of course, if somebody thinks it's enough, please come to talk to me. I'll be glad to get explanations. Exploit mitigations. I was talking about how people think they can write or generate exploits automatically. In fact, when they do such thing, they always do it in what we call a restricted model. A restricted model is an academic exercise where mitigations are ignored. So you can, for example, generate a stack-based buffer overflow exploit ignoring the fact that you have control flow integrity, or ignoring the fact that you've got depth execution prevention. Of course, before, I call it depth. Sorry, I worked for Microsoft for many years, but in fact, all the credit goes to the PAX team that came up with page exec and segment exec and then kern exec in the last 15 years. It's been also a real pleasure to test these PAX security extensions to the kernel in the past 15 years. I think I've been an early adopter of PAX, and I definitely encourage you to use it in your machines if you rely on Linux today. So many kind of exploit mitigation that are supposed to protect from exploits and that do a pretty good job in practice, but attackers come with more and more capability. Then it's they keep bypassing things, and then it's kind of a cat and mouse game where everybody's trying to top the other one. And so we've got these data execution prevention and address space layout randomization, but people are coming up with new mitigation as well. One is control flow integrity that I'm going to define a little bit more in a second. Another one is called intra-modular displacement randomization, and I'm going to talk about this a little bit as well. Opposite to the restriction models, I like to call that the full models, the full automated exploitation models, where in fact your AE algorithm actually take into account all these protections that the operating system provides to you. This is, of course, a much harder problem than the below. And nobody today in the world have tackled these problems. People are trying, but it's clearly an open problem today. And this is the topic of this talk, exploit generation in full models. Control flow integrity. Control flow integrity is not a new technique. It's something that has been researched and also implemented in the past 15 years, 10 to 15 years. The very early implementation of control flow integrity that I know of was done by a company called Determina. And at the time, they called it program shepherding. More work was done by Martin Abadi to kind of formalize it in the academic way, and plenty of people are trying to come up with more practical approaches to control flow integrity. What do I mean by control flow integrity? So control flow integrity means that if you have a program, the program has a control flow graph and a call graph, then it's not possible to make the program diverge from this execution flow. For example, if a function A is supposed to only call function B, then under a CFI process, it's not going to be possible for function A to call function C. Likewise, it's not going to be possible for function B to return from anything else than A. So if A calls B and B calls A, and this is the only relationship you have on a control flow graph between A and B, then A is not going to be allowed to call C, and B is not going to be allowed to return to anything else, for example, D. You also have a stronger version of control flow integrity where within a function, you wouldn't allow, for example, indirect jumps, for example, that goes from one block to another without having respecting this original flow, even though from what I saw, most of the implementation tractable one, the one that can work with enough minimal performance overhead, they work at a call flow level, which means between functions. So the consequence of that, we don't really have a control flow integrity in place today. But people are working really hard to get this done. In the next few years, CFI is gonna hit the mainstream market. And the consequence of that is that if somebody, for example, wants to erase a function pointer and to point into a raw payload, or even overwrite a return address, it's going to be harder because protections are going to be in place. Maybe even hardware supported protections to actually enforce strict transitions on the control or call flow graph. So this is going to be a big problem for exploit writers in the future. Another mitigation that Matt Milliken, Johnson, Nick Goyle, and myself came up with 2 years ago, also inspired by many other people's research, is something called IDR, intramodule displacement randomization. The core idea of IDR is the fact that we need to have randomization within models instead of between models. So when you say ASLR, you think, oh, I'm going to randomize the base addresses of DLLs, for example, or libraries that are being loaded. But it means that if you have one information disclosure within this model, then based on the base address or whatever else address in the model, you're going to be able to predict the address of all gadgets, of all instructions that you might want to use in your raw payload within that model. So this is kind of a problem because it means that one information disclosure is a game over for DAP and for ASLR. The idea of IDR is to inject some kind of randomness within a model, for example, between functions. It means that if you have an information disclosure that is targeted to a specific function, you have no idea about the exact address of some other function within that model. For example, you can add some padding at runtime between the function, and the padding depends on some random parameter that you choose at relocation time, for example. We have there are prototypes of this protection already, even though, again, it hasn't hit the mainstream market. People have been working on that really hard to make it happen and to make information disclosure a harder game. In other words, if you see these guys, especially these guys on the right who looks particularly shitty, if you ask me, you're all covered, don't worry about it. It's all, this guy like here, like you see. Anyway, which one do you trust more, by the way? I don't know. And, with those protections, it becomes extremely hard to generate exploits. It's already very hard with DEP ASLR, but with CFI and with IDR, it's becoming another new level of challenge. However, we have a few tools. We worked on a few different tools, and I'm going to present some of them, and I'm going to introduce some maybe new ways of thinking about this problem that can help offensive researchers, hackers, to start thinking of how you can actually bypass those things. And the kind of new techniques of exploit that are going to show up, that are already existing, but that are going to become mainstream in the next 3 to 5 years. What kind of tools do people use today to do vulnerability automation or analysis automation, if you like? Some people use compilers. T-Patch actually gave a 3-hour talk 2 days ago about that. It was very informative, even though people were kind of trying to sleep after half of the talk, but that's okay. We were talking, the two of us, anyway. That was a really great talk, by the way, thank you. People use compilers to insert transformation phases so that they can infer, they can deduce what the program does, or they can enforce some checks in the program by directly, modifying how the compiler behaves. This means that you can add checks, that are going to be, you can add assertions that are going to be checked in runtime, or you can add assertions that are giving you feedback on some particular information and plug that with some other tools. For example, fuzz testers. Spender has done some interesting work that I'm looking forward to understanding more on interfacing fuzz testers with compiler transformations. You got SMT solvers. SMT solvers, I'm going to talk about this a little bit. Not too long, because I could pass the whole day talking about that. But SMT solvers have been a really popular tool in the past few years due to the increase in computational power. And we'll see that SMT solvers can definitely resolve some problem, not every problem, but some problem can actually be resolved using those solvers. Model checkers. model checkers is another kind of formal tool or formal technique that relies upon state space exploration. So state space meaning, when you say a state of a program, you mean all the value of the variable of a program. So you've got a huge array of all, the memory content, and then you've got transition between that memory content or, memory model. And basically, updating a variable means updating the state of this program. Model checker relies on making this state space explicit, which means it's very memory consuming. It doesn't scale so really well usually because you got to explore the whole state space of the program, and state space for very large programs such as operating systems can be extremely large, and in fact it's totally intractable to enumerate the whole state space. So people have tried to introduce new kind of tools. For example, symbolic execution engines. People have worked on things like AEG or like something that they called mayhem. Oh, funny, guys. So these kind of tools are basically smart fuzzers that can track information that are not necessarily related to the value of variables, but also the symbolic value of variables. For example, you can define a domain for variables that is not in the program, but that is kind of a meta-level domain where you track only the signs or only specific information like taintedness. Is that variable actually user controlled? You've got a bit, like a meta bit for each variable says, oh yeah, this is tainted or it's not tainted. It means the user is going to have an influence on this variable. And of course, we're not just talking about the top level variable like the parameters or functions, but very, very deep variables within the program or operating system. And things, you've got other things, emulators. People try to use emulators to do some kind of analysis, like Box. Box is a pretty good emulator. And also abstract interpreters that are kind of, I would say, emulators that work with an abstract domain. So they abstract from the whole program and create a state space that is abstract, only retaining particular properties of the program that matters for the particular things you want to check in a program. This has been pioneered by Patrick Couzeau in École Normale Supérieure in Paris for 30 years already. Even more than that, it's getting old. Anyway, all these techniques are the kind of techniques that people are going to try, are starting to use for exploit generations or vulnerability analysis, and are going to have a bigger and bigger role in the future. Let's talk about one such tool, SMT solvers. So just in a nutshell, SMT means satisfiability modulo theories. What that means is that you have a formula, you have a logic formula like that, first order logic formula usually, and you try to give a value of variables for which this formula is true. The set of values of variables for which the formula is true is also called a model. So when I talk about a model for a formula, it means the value of the variables. Usually those are Boolean variables, so they can only be true or false. But there are ways to encode complex things using only this encoding. Obviously, you can do integer arithmetics based on that. If you have an arithmetic theory, for example. Two examples of that is the following. So at the below you have an example. B is bigger or equal to A, and A is smaller or equal to B. This is a satisfiable formula. Why is it satisfiable? Because in the case A equals B, then the formula is true, right? Both constraints are possible at the same time. In the second example, it's an example of very simple unsatisfiable formula. For example, you say A is true and B is true, and also A and B is not true. This is clearly unsatisfiable because if A is true and B is true, then A and B is true. So if you have such a formula, it's unsatisfiable. For example, you are analyzing a program and you try to find which path is feasible, and you collect all the predicates, you know, of the ifs and the else, and you collect them as you go, you analyze the program, and if you come to collect those things, and you pass it to an SMT solver, it tells you, oh, it's satisfiable, which means the path is feasible. Or it's not satisfiable, okay, that's an infeasible path, let's just discard it for the purpose of the analysis. An example of SMT solver is D3, it's done at Microsoft Research, and it is one of the most efficient solvers today. It's a very powerful solver, and the reason why it is so powerful is because it accepts new theories, where the modulo theories come from. It means that it's a satisfiability solver to which you can add new ways of reasoning about formulas. For example, you can add arrays, you can add functions, you can add bit vectors. So it's not just Booleans saying if the group, like the set of Booleans of Boolean formulas are true together. It's also a very powerful tool to actually reason about programs and systems in general. There is a very nice online site where you can actually try D3 for yourself, and I may have enough time to actually go there. An example, a very super small example and super stupid example is the following. When you have a C program on the left, it just does nothing. There's just if C is smaller than 10 and ret equal 1, otherwise ret equal 2, okay. The way that it's going to be translated into a SAT formula, SMT formula, is by doing the following encoding. So first you've got 3 declarations, the X, the ret, and the C. Those are just variable declaration or constant declaration. And then you've got the logic of that piece of code being encoded. So what that first thing means this first formula means is sorry. What this first formula means is, oh, if C, so you gotta, this is reverse Polish notation, which means, in fact, you should put, this, so this is an implication, right? It's not equal or bigger, it's an implication, a logical implication. Because if you want to do bigger or equal, you gotta put the equal on the other side. That's a kind of interesting point. This first assert means, oh, if C is bigger or equal to 10, then ret is equal to 2. Okay? It doesn't say that this is true. It says a relationship between the variables of the program, right? It means, oh, I infer because I translated this program into this set of formulas, I can actually say, oh, if C is bigger or equal than 10, then I know that ret is going to be 2. Oh, by the way, and if C is smaller than 10, I know that ret is going to be 1. Okay? And the third one is like a check. Let's say, at the end of the function, I want to check if it's possible that ret equal 1. What are the values of variable for which it's possible to have ret equal 1, given all these constraints, right? So we model the program using formulas, and we have some additional assertions we want to check in the program. For example, an annotation in the program, we might want to check that an array is never accessed out of bound, or whatever else, the size of a malloc is never 0, or the pointer is always validated before it's dereferenced, and things like that. You encode asserts as well. And then you've got two functions of the solver. Check stat. Check stat is going to tell you yes, this set is feasible, or it's not feasible, it's satisfiable or not. And get model is giving you the value of variables for which this is true, if it is true. In that case, the result is going to be, yeah, that is true. All these conditions can be true at the same time. And in which condition can they be true at the same time? Get model tells me, okay, when C equal 9 and ret equal 1, then everything is fine. All these assertions are provable at the same time. So let me see if I can actually I'm terrible with Mac, so maybe I don't even know how to reduce that shit. Okay. All right, so if you go to riseforfun.com/z3 or even z3.riseforfun.com, you can do that online. And this is not going to be... And if I had the right amount of size, I would be able to show you that you've got a small button that actually solves these formulas for you and give you the model. Yeah. Does anybody know how to view the below of the screen when I'm Nope. Oh, okay. Here you go. Thank you, FX. Okay. So you've got these things, and you click on OK. You click on the little play button, and it gives you the model for these formulas. For example, let's say I wanted to have rate equal 2 instead of rate equal 1 in my assertion checking. I just change that. I say, okay, give me the model for which all these formulas are true. But this time I want rate equal 2. I execute again, and here I see, oh, now if C equal 10, rate equal 2, and it gives me one model. It doesn't give me all the models possible. It just gives me one for which those formulas are possibly true all together. I use such a thing on 40 million lines of code of Windows. It's a very slow process when you have so much code. Obviously, I just give you the dummy version of that here because otherwise we're here tomorrow. But basically, such a tool is a very nice way of representing what the logic of a program is without... Yes, sir?
How slow was the
slow? It's... I had a 48 cores machine with 96 gigs of RAM. And in order to analyze 40 million lines of code, it takes about 10 hours of checking. And it's, if you wanted to have inference, as I had, which means propagating state between functions, okay, it took me about 20 hours. So it's slow, but it's a lot of code, right? It's much slower than a compiler for sure.
Yeah, sure. But it's not like years of time.
Pardon?
It doesn't take years. It's just
Oh yeah, no. It's like I had a daily round trip, I launch my analysis when I go to sleep, and then in the morning I'm like, oh, where am I at now? Oh, I've got 2 0 days today. Anyway. Nice. Okay. The tool that I've been working on a lot when I was at Microsoft, and I left Microsoft 1 year ago, so I don't work on this anymore, but I work on this for 4 years. And this tool called Havoc is a verifier for C or C++ programs. It's pretty complex in the way it works. It translates to particular intermediate representations, which then translate to these formulas, to the SMT formulas I just showed. And then this trick gives you, input models, which mean that, if you want to generate an input, for example, to reach your assertion, then an SMT solver can actually help you do that. We found more than 100 security vulnerabilities that were fixed in Windows, in the kernel, and Internet Explorer, as well as Windows application code. Many different properties we checked. 3 or 4 months ago, I presented an article at Oakland, in the Security and Privacy Conference in San Francisco, and there is a paper called Towards Practical Reactive Security Audit Using Extended Static Checkers that describe the whole experiment on 15 pages. If you want to take a look, please do. I'm not going to do that right now because of lack of time and because of the topic is so different today. But that was certainly a nice experiment to see what's feasible and what not. Before I go forward, do I have any question on that? No? I'm sure we're late, so we're going to go forward. Okay, so the problem of SAT solvers, SMT solvers, is the fact that they model very deterministic behaviors of programs. It's not possible using, or it's very hard, it's not natural to actually model non-deterministic behaviors of programs using an SMT solver. An example of non-deterministic behavior of a program is the heap, especially in the presence of heap randomization. In the last Windows 8, some of you may have seen that you got new heap randomization tactics, for example, a sub-segment randomization, things like that, where you've got a certain heap segment, and you'd say, oh, if that segment is 80% full, then automatically I'm going to allocate a new segment or a new sub-segment instead of trying to fill as much as I can in that segment. By doing that, you ensure that an attacker does not have the ability 100% time to actually fill an entire segment or sub-segment of the heap, which gives him more ability to actually align the chunks properly to get, say, a function pointer to be erased for a heap based on a heap overflow or something like that. So because you have this non-deterministic behavior of the heap, sometimes you're going to have cases like that. Oh, now, and even without protections, you can even have that. 90% of the case, you know, I'm going to have state 1, a state of the heap, which is, oh, first chunk, and then second chunk, and then third chunk. You know, we've got address A1, A2, A3, and the size S1, A2, A3, and I should have named the size something else because it confuses everybody with the name of the states. Let's call, on the left-hand side, let's call them P1, P2, or small s1, small s2. In some cases, you're going to have the chunks aligned like that. But in some other cases, because, you know, the malloc or freeze or whatever coalescing operations didn't happen in the same order, then you're going to have it like that. So if you had, say, a function pointer in chunk number 2 to erase, and your overflow was in chunk number 1, in the second case, where in 10% of the cases you have different alignment, then your exploit is not going to work because you've got to erase chunk 3, and then because of the non-determinacy of the heap, your exploit is going to be unreliable. So this is the kind of program that SMT solvers are pretty clueless about. SMT solvers are not enough to resolve that. An idea is to use, you know, more like probabilistic modeling of programs. You got something like Markov chains, which are the idea, the core idea of Markov chains or Markov processes, Markov networks in general, is that it might look very random and chaotic to look at a program from very near. You know, you see events arriving and you're like, oh, this looks random, you know, like there is no pattern in there, there's no structure in there. But if you look from the back, if you take a step back, then you start to see some kind of structure. Even though, you know, it's not a deterministic structure, you can have a non-deterministic structure of a program. So let's talk about that. Let's give you an example. You know, I had given like 2 states. You had state 1 and state 2 of the heap with the 3 chunks aligned in a different way for each state. And you have transition, for example, a new heap primitive is executed, a new malloc happens, a new free happens, and things like that, which means that the heaps change state with a certain probability. So let's start by whatever state, S1, and we know that with probability 0.9 it goes to S2, and with probability 0.1 it goes to S3. And then you got another heap primitive being executed, and then it goes to another state one more time. It's possible to actually compute the multi-step probability of a state reachability. Say, I say, oh, what is my probability of reaching state 4? Because I know state 4 is an exploitable state. I compute this probability. I say the probability of S4 below, the very first line. The probability of reaching S4 from S1 is the probability of S4 being reached from S2, knowing S2, which means like coming from S2, multiplied by the probability of reaching S2 coming from S1. In that case, there is just one path to reach S4, so that's the only probability you have to compute, which means 0.6 times 0.9, which gives you about 55% chance of reaching this particular state. You have, say, S5. You know that S5, you know, is another exploitable state. Of course, it answers different list of heap primitives. You got to do different lists of malloc and freeze and other heap operations that are different in order to reach S5 than you have to do in order to reach S4. For example, you can do S1, S2, S5, or you can do S1, S3, S5. What is the probability of reaching S5 from S1? We can compute that again. Oh, the probability of reaching S5 is the probability of S5 knowing S2 times the probability of S2 from S1, and you also have another path. You have the right-hand path. You got to add the probabilities this time, and it is the probability of S5 from S3 times the probability of S3 times the probability of S3 knowing S1. And you do multiply, you do the same operation, 0.9 times 0.4 plus 0.95 times 0.1. When you add this all together, it gives you 145.5, which is 45%. So if you had the choice, if you had an exploit, and you were trying to maximize your probability of reaching an exploitable heap state, you know that it's actually better for you to try to reach S4, even though you know you got more paths to reach S5. In fact, the probability of taking the path that reach S4 is bigger than the probability of you executing in a path that reach S5. And by probability, I mean, you know, the amount of input, the combinations of input that are going to allow you to reach such a state. So you might have, for example, 54 different combinations of input of the program that allows you to reach S4, while you only have 45 combinations that reach S5, imagining that you have 100 input combination in that case. So this is the kind of reasoning we need to put into work in order to be able to work with exploit non-determinacy. We don't have tools to do that yet. But there is some hope. It's questionable whether such a technique can be purely static. It's very, very hard to infer these kind of heap transition models in a pure static manner. You can run the program in a debugger, instrument the heap primitives, and gather information on, you know, the statistic on the correlation between input and execution of heap primitives and reachability of a particular heap state. You can do that. And then, depending on your monitoring, on your sampling, you can choose a probabilistic you know, input that's going to reach a particular state with the most chance. We haven't resolved today. There is no generic tool to do that, but I believe it's something that people are going to work on in the next few years as well. All right, this is the last part of the talk. How much time is it? How much time do I have left? $10 minutes? Not sure. Okay. All right, I'm going to go forward, and then if I don't have enough time, please let me know, because I unfortunately didn't keep track of time. So I created a set of challenges that I believe are describing very important problems for the you know, automated exploitation grand challenge. And I'm going to talk about these now. We restrict ourselves on the full model. As we said, we want to take into account those mitigations. We've got some related work. For example, Julien, he created a master thesis on a restricted model, automated exploit generation. We've got David Bromley at Carnegie Mellon and his team, who wrote a series of papers about their tools that can actually generate exploits in restricted models without taking any mitigation into account. It's mostly academic, you know, it's more academic than anything else. I don't think you're going to be ever able to use those tools to generate a real-life exploit. But, you know, they're trying to dig into a new research area, so let's give them some credit for it. Okay, the big inspiration of this challenge is really Hilbert's program. Hilbert is a German mathematician, and more than 100 years ago, he came up with a list of 23 hard mathematical problems that were really touching the foundations of mathematics. To this date, 5 of these problems are still unresolved. Of course, I think my problems are going to be resolved much earlier than that. Also, I hope. But if you want to know a little bit more about Hilbert's program, I refer you to this Wikipedia page that is greatly informative. This I already said. The perimeter. So when you do a grand challenge regarding vulnerability discovery or exploitation, you've got some way of measuring a solution that you have to take into account. For example, how sound is my solution? Is that precise? Does it have a good signal-to-noise ratio? How many false positive, negatives do I have with such a solution? We're talking about undecidable problems here. So it's inevitable to have some false positives, at least a small amount. You can also choose to have no false positive at all, but in fact, you're going to have lots of false negatives if you do that. It means you're going to miss lots of bugs. Because you want to focus on the most certain bugs, you're going to miss lots of bugs. Or if you really want to find all the bugs, then you have to accept that some of the bugs you're going to report are actually false bugs, not true bugs. And same goes for exploit. You're going to generate inputs that are not reaching your particular vulnerable state, but because of the way you actually came up with the input in the first place, you got to accept the fact that strategies are approximate. The expressivity of a solution is whether a solution is parameterized or parameterizable, which means, is that a hard-coded solution I have for this particular case, or does it work for the whole family of cases that are induced by this generator, for example, or like this example of problem. The scalability is also very important. Does your solution work only on 10 lines of code, or does it actually work on millions of lines of code? So it's important to come up with scalable solutions so that you don't resolve problems in isolation, which might look great on the paper or for an academic publication, but in practice will not lead you very far. The completeness related to coverage. So if you have a path or an input or a context that is feasible in the program, are you going to be able to reach that? Do you have enough coverage? It's different than scalability because you could be able to analyze so much code but not have much coverage. Maybe your tactics make you that you don't explore some particular state space of the program or subset of the state space of the program because of your choices. And resilience, this is kind of an esoteric aspect of that grand challenge because we're talking about exploit generation. Is the solution resistant to environment, to mitigations? Is that only bypassing one mitigation or all mitigation at once? All of these have to be taken into account when you think of a problem. Okay. Problem A, I think we define the concept of state. This is the most simple problem you can have. Given a state, what does it take? What is the input that it takes to reach a particular assertion in the program? I'm going to give you an example just after that because I know it's a little complicated to actually understand just by the description of the problem. I'm going to be very explicit in a second. Problem A, you got an initial state of a program, you got an assertion somewhere in the program. What is the input I have to craft in order to reach this assertion, in order to falsify the assertion? That's a very hard problem. People like Patrice Godefroy with the SAGE project at Microsoft Research have been working very hard on that, and they only reach about, at the very maximum, 90% coverage. So there will be like cases, in a certain amount of cases, they won't be able to reach, even with their constraint toggling algorithm they have. So it's still kind of an open problem, even though it's certainly the less open, the most tractable of all problems I'm going to present today. An example of that is you got a function, okay, and you want to know, what is the input I have to give to the program to f, in that case, in order to satisfy or to dissatisfy this assertion. Because I know that if index is bigger than the size of the location of the array, then I'm going to start having array out-of-bound accesses, array out-of-bound writes. I'm going to be able to write 0 bytes in memory. So what is the value of x and y I need to give in order to be able to falsify this assertion, to make it false, so that the program is insecure? This is a very stupid example, small example, but then if you think about it in terms of scalability again, you're going to have huge programs, a huge call graphs with like 20 function deep call graph. And it can become a very hard problem to do that properly because you got to track lots of things, really a lot. So this is the first problem that I called exploit reachability. Second problem, exploit derivability. It's almost the same, except that given, for example, you have a fuzzer, you have a fuzz tester, you generate a lot of crashes, and you found out that, 80% of your crashes are null pointer dereferences. Oh, is there a way you can take these traces, these back traces, these stack traces, and try to mutate a little bit these traces in order to reach a more exploitable condition than the null pointer dereference? Not like null pointer dereferences have always been non-exploitable, by the way, but let's assume they are. You have a program, and you have a state that's not the initial state, that's some state of the program where you have a crash, you have the back trace, you have the stack trace of this crash, and you want to know what's the prefix of this stack trace that you have to take in order to build another postfix or suffix of the trace and reach another more exploitable condition. As you can see, the difference in problem B. Example of that is the following. You have a function, and with a certain combination of x and y. For example, if x and y are small or equal to size of lock, you're going to be able to write into an array. Otherwise, you just read the array. Okay. Otherwise, you just read log x plus y, the index of x plus y. Clearly, you can see if x plus y is equal to size of lock, here you're going to have a off by one access to the array. So there is just one input that allows you to have a write primitive. For every other input, you might have read primitives. You're going to be able to read something, but obviously from an exploit perspective, it's better to write things than to read things. So in most of the cases, you're going to read out of bound, which is not very helpful for an exploit, but in some very particular case, you're going to be able to write. So let's assume you take 99% of the time, you take the path that does not enter the if, and you crash at the read access. You got these stack trace, or you have the list of instruction, you execute it. What is a prefix that you can take of this list of instruction so that you can divert from the original crash just a little bit so that you turn this crash into a more exploitable crash? For example, the one that writes out of band. So that's another problem. Of course, again, that's a very small example. Imagine that in very, very big programs, which is what we're working on. Third problem is what I call multi-trace exploitation. Sometimes an exploit is not, and most of the time I should say, an exploit is not just a one straight trace. You have to execute one thing, corrupt the program, and then there is a corrupted state somewhere lying in the program, but it's not an exploit, it's just that some variable has some value it shouldn't have, but it's not exploitable. And then there is another way of executing another trace of the program that is going to make use of this corrupted variable and then trigger a real exploitation vector, for example, a write primitive or something like that. Let me give the example straight away because it's not always easy to bear with my formalization of these problems. Let's say you have two functions. You got f and you got g. One function does glob equal malloc x plus y. If you do static analysis function by function independently, you're never ever going to figure out that there is a problem there. Because doing malloc x plus y, is not necessarily a bug at all. It could be that there is some constraint at the precondition, at the input of f that makes x plus y never overflow, or it never zero. So it could be that there's no bug at all if you analyze f and g in independence. However, if you're able to craft an exploit that concatenates an execution of f and an execution of g, you can see that, if I have an integer overflow x plus y, or if x plus y is actually 0, then when I execute g later on, I'm going to be able to write a 0 at some place out of bound of the heap. Independently, with like local analysis, you can't find that. You gotta actually, and it's not even a trace, it's not even f calling g. if it was like that, you could use inter-procedural inference to do that. You could like pass state from one function to the other and then track this information that you need. But here it's like two totally different execution traces. For example, you've got one system call in the kernel that's going to corrupt the state of the kernel, and then another system call that's going to reuse some internal value of the kernel in order to dereference the pointer. You need to know what are the two syscalls that are related here. It's hard to do that because the explosion possibilities are really huge. So that's another problem that people have to resolve in an efficient way as well. The fourth problem is something I call precondition inference. There has been some work as well in this area. And the problem is the following. Given an assertion in the program, what is necessary and sufficient condition at the beginning of the function, or ideally at the beginning of the program, that is going to make this assertion false. So at the very problem, if you remember, we had a very forward kind of vision of things where we say, okay, I start by the initial state, I go down to the program, I'm going to try to explore the program like that. Here, precondition inference is the equivalent of that backward. So you got an assertion, and you want to know, what are the input of the program that I need to give in order to reach this assertion and make it false. An example of that is the following. You got an assertion, index is smaller than 4, and you say, oh, but, what are the conditions at the beginning of f in order to make this assertion false? Or you realize, in fact, that in order to do that, you need to know what is the post condition of g. Okay, what are the conditions at the end of g in order to have index smaller than 4. So in that case, it's trivial. It's just, oh, the return value of g has to be smaller than 4. And then, given that post condition of g, what is the precondition of g? Because, f calls g, so you can't analyze f in independence of g if you want to resolve that problem. And then you come back and you say, oh, of course, in fact, I need to have, for example, x bigger than y. If x is bigger than y, then we're going to return 0, which means 0 is smaller than 4, everything is fine. So that becomes the precondition, necessary precondition of g. And then you come back to f. You say, okay, given that precondition of g, what was the precondition of f that I wanted to have? This is, people can do this forward with very simple templates for pre and post conditions, but doing it for any assertion is a big problem. So backward inference, that's another problem. Another problem is loop invariant inference. My dear friend Thomas Julien last year gave a small problem related to that, and I gave a solution that was not entirely automated, but a solution that allows you to basically analyze loops and every iteration of the loop to guarantee that the loop is doing something right at every iteration, every execution of it. Given a loop, an assertion A1 inside the loop or after the loop, what is a loop invariant A2? The loop invariant means what is a condition of the loop that has to be true at every beginning of iteration in order for this first assertion A1 to be true or false, true in that case. So again, hard problem to do statically. Maybe you can do it dynamically, even though I have reasons to think it's not possible to do dynamically for exploit writers. The example is the following. You got a function, you got an assertion, you say, oh, what does it take for the loop to have, at the end of the loop, have I smaller than size of buff? What are the constraints happening on I in order to make this happen? You see that the loop has index, and there is a limit. The limit is, say, the size of the buff. But then in some conditions, the limit changes. If the loop is just an iterator of the buffer, for every character, it tests if it's an opening bracket or closing bracket. If it's an opening bracket, just increase the limit. If there's a closing bracket, decrease the limit. So clearly, you can see if somebody puts a lot of opening brackets in that buffer, you're going to have I that's bigger than the limit, which means it's going to be bigger than the size of the buffer. How do you formalize that automatically? How do you infer the loop invariant So the loop invariant here would be, oh, buff 0 different than opening bracket, and buff of 1 is different than opening bracket, and etc., a very long list of conditions for every single character of the buffer, and you have to say, oh, in fact, what has to happen here is that every single character of the buffer is different than an opening bracket, or an even better way of saying it is, oh, the number of opening bracket is smaller than the number of closing bracket. If you have this condition, then you can guarantee that I is always going to be smaller than the size of the buffer at the assertion point. But it's hard to actually synthesize these kind of conditions automatically. If you have an expert guiding, the SMT solver, for example, to understand what kind of condition has to happen, it's a lot easier. But if you want to do that automatically, it's very hard. One more problem, and we're almost there. We should have coffee. Heap likelihood inference, I'm going to go really fast on this one because I've talked about it already with the Markov heap modeling. Given a program P and a heap allocator A, let's say you have a write primitive, you have a chunk that you can overflow. What is the most exploitable random walk for the heap write primitive? By random walk, I mean what is the sequence of heap primitives that you have to execute that gives you the most probability of reaching an exploitable state. That's exactly what I said when I was talking about the Markov Chains and others. You can try to do that statically. I have my doubt on this feasibility, or dynamically. If you do it dynamically, I guess there is a chance that people are going to come up with that kind of analysis in the future. We don't have tools to do that today. Another problem we have is the ability to infer addresses or even values or sizes of variables based on timing measurements. People have tried doing that, and they did that. For example, Paul Packett gave a really nice talk at SummerCon this year in New York, and he showed how he measured Firefox executions in order to deduce the value of particular pointers just based on the time it took to actually execute the JavaScript code that he could give. It was relying on a very particular pattern of like chosen hash insertion elements, and the fact that a hash table could hold both user-defined input and also internal pointers of the program. So that was a very particular limited solution of that problem. But basically, what are the conditions? The problem is, what are the conditions that allows you to infer, to find, to measure indirectly, just by time measurement, what is the address of a pointer or address of a variable, the size of a buffer, say it's a dynamically allocated buffer, what is the size? The size may allow you to get the address of the next buffer, or of the buffer itself, because you have multiple lists of chunks, obviously, in the heap management. So you might have a hint on which list is going to receive your chunk if you know the size of that chunk. This applies to lots of different data structures. You can apply this for heap chunks, for stack frames, for global variables, and all that thing. So if you measure the program and you can't read the program, you can just measure the time of the program. What can you deduce? Can you deduce the address of an instruction? Can you deduce the address of a function or a method, etc., etc.? So purely time-based, without being able to have an information disclosure, without being able to read the address space of the program, just measuring the time, what are the necessary and sufficient conditions to determine the address of a resource? Another one is concurrent program analysis. The big problem in concurrent program analysis is very similar to the one in model checking, is a state space exploration. Especially, excuse me. Do I have any questions before that? Concurrent program analysis. What is a good way of factoring the state space of a program when you have multiple threads? If you have two threads, you have one state, and you have two possibilities of scheduling. You know, you have thread 1 and 2. You have one instruction executed in thread 1, and then you can continue to thread 1, and then or schedule to thread 2, and then on that one you can continue to thread 1, schedule to thread 2. So you got an exponential state space explosion as you have threads. Basically, if you have threads at every single scheduling point, you're going to have n possibilities of scheduling. So it's n times n times n times n times n at every single instruction, which is massively exponential. Is there a way to actually represent the state space of a concurrent program in a way that's tractable for analysis without being limited to like 10 lines of code? Some people came up with things like partial order reduction to help this, even though the problem is far from being resolved. So that's a big problem we have to resolve, the factoring of concurrent programs. State space of concurrent program, that is. And the very last problem, and it's a bonus problem, it's not a very necessary one, but it's something that would be really great to have. We got more and more, we got multi-stages exploit. We've got one exploit that hits the browser, and then from the browser you try to hit the kernel. Or maybe you have a sandbox, an exploit that actually break within, you know, the browser from within the sandbox, and then you got to get out of the sandbox. So you got a two-stage exploit, even not touching the kernel. Is there a way to determine what part of a program actually run in a particular privilege level? Of course, dynamically, it's trivial to do that because you just measure, you just check your seeds or things, something like that, and your security identifiers, and you check what kind of privileges you have. But can you do that statically? Sometimes people actually write functions that can execute at multiple privileges level. You can have a function that execute, sometimes in low privilege level, sometimes in high privilege level. So where do you draw the line? Where is the intersection? This is helping you, is going to help in multi-stage, like automated multi-stage exploitation, because you need to figure out what to attack next. Right? So that's another thing that somebody has to figure out. All right. We're almost there. I just have a concluding slide. But after all of that, you guys are pretty much set, right? You are the new automated exploitation expert in here. And what we all have to do, I'm sure you guys saw the same thing. Basically, yeah, it's going to take a lot of nights without sleeping in order to even resolve one of such problem. I believe it's going to take at least 3 to 5 years, if not more time, to have some good progress in that, even though it's going to be very fun. People don't expect this to work quite soon, but at the rate of things, it could very well be possible that in like 3 years from now, people actually do have a few hints on that. Tomorrow, exploit techniques. One, and it's already happening today, data-only attacks. Because we're going to have control flow integrity mainstream. It's not going to be possible to corrupt return addresses anymore. It's not going to be possible to corrupt function pointers anymore. People are going to try, and they do it today already. It's going to just become extremely necessary, and everybody is going to do it in the future. Only attack variables. What can you do when you attack variables? For example, you can try to write your tokens. You can put a token of the Windows kernel to null in your list of tokens, which grant you all privileges. You can write for if you are in Internet Explorer, you can change the zone in which your code is executing, which means you can potentially instantiate an ActiveX control from an untrusted site, things like that. So not anymore modifying the control flow program, simply change variables. They do the address of the variables that you have to change that is going to give you more privileges. Like, another basic example, if you have a authenticated or authorized flag, Boolean in the program, if you have the address of that and you're able to change it from false to true, then you become authenticated. This is a kind of data-only attack. another kind of family of attacks, and this is totally made up by me at 2 o'clock in the morning. It's program likelihood inference, and I gave an example of that, you know, with the probabilistic attacks that people may try to do in the future. Another one is a timing attack that Paul Packett and Dan Blazakis actually presented this year. And of course, it is all inspired originally by, you know, crypto attacks by Kosher, and, you know, all these timing attacks that allows you to retrieve pieces of the keys and everything. These guys translated it into an exploit landscape. They use this kind of technique to actually deduce things that they can use in exploits. So that's a new way of thinking of how to write exploits as well. To conclude, we decompose the problem of automated exploitation in a set of challenging problems, and those problems are not going to be resolved anytime soon, especially because the general problem is an undecidable problem. It's not going to be possible to do it every time, but people can actually try to do it sometimes. What are the conditions? What is the perimeter of this domain of possibilities? With this, I'll just take questions, and thank you very much for your attention.